There are only so many ways to arrange the atoms of a human body. That number is almost too large to hold in the mind, but it has an edge. It stops somewhere. And that single fact, that the number of ways to build a person is finite, while the universe, as far as our best instruments can tell, may not be, is the reason a small and serious group of physicists have started saying something that sounds like fiction, but is argued with equations. Somewhere out there, beyond every galaxy your telescope will ever catch, the exact arrangement of atoms sitting in this room, reading these same words, may already exist again. This is why the flattest measurement in the history of physics, a single number pulled from the faint afterglow of the Big Bang, has quietly turned into one of the strangest ideas modern cosmology has ever produced. The idea that there is no such thing as only one of you. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath, and let's begin. Ordinary life already runs on a version of this uncertainty, even if most people never notice it. Weather forecasters have known for decades that the atmosphere is sensitive enough to tiny disturbances, a shift in temperature too small to feel, a gust of wind too faint to register, that two nearly identical starting conditions can lead to completely different storms only a few weeks apart. If a system as large as the entire atmosphere of a planet can be steered by differences that small, it is worth remembering that the smallest differences of all, the ones quantum mechanics describes, are constantly rippling upward through every physical system that exists, including the ones sitting inside your own skull. That fact alone, long before anything about distant galaxies or branching universes enters the conversation, hints at how thoroughly uncertainty is woven into the basic architecture of reality. It is worth being clear about what tonight's argument is not, since ideas about other versions of a person show up in plenty of places outside physics, story, myth, and casual speculation among them. What has been described here does not rest on any claim about fate, destiny, or a plan behind the universe. It rests entirely on measurement, probability, and equations that have been tested against reality far more rigorously than almost anything else humans have ever produced. The distant twin discussed tonight is not a spiritual double or a symbolic alternate self. It is, if the underlying physics holds up, an ordinary arrangement of ordinary atoms, following the exact same laws that govern everything from the fall of an apple to the burning of a star, simply located somewhere too far away to ever reach. Stripped of any mystical framing, the claim is almost mundane in its mechanism, however extraordinary its implications turn out to be once followed all the way through. Everything that follows starts from somewhere ordinary, a single planet tucked inside one spiral arm of an unremarkable galaxy, circling one ordinary star among hundreds of billions crowded into the same disk of stars and gas. That galaxy is one neighborhood inside a vastly larger structure. Groups and clusters of galaxies, bound loosely together by gravity, strung along filaments that stretch for hundreds of millions of light years, with enormous, nearly empty voids carved out between them. Zoomed all the way out, this entire arrangement, every star, every galaxy, every filament and void combined, forms the sphere astronomers call the observable universe. And even that, as it turns out, is only the smallest possible beginning of the actual story. The idea that there might be more than one of everything is not new to modern physics, even if the equations behind it are. In the late 1500s, the astronomer and philosopher Giordano Bruno argued, well before telescopes existed, that the stars scattered across the night sky were suns, much like ours. Each one likely surrounded by its own worlds, spread across a space with no edge and no single center. The idea was radical enough at the time to draw serious hostility, and Bruno never had any instrument capable of checking it. What is striking, looking back, is how much of the basic intuition turned out to hold up once real telescopes and real measurements finally arrived centuries later. Stars are indeed suns, planets are indeed common, and space, as far as anyone has ever managed to measure, does appear to extend far beyond whatever boundary earlier generations assumed it must have. Tonight's argument follows the same basic shape, an old intuition about abundance, now backed by actual measurement rather than philosophical guesswork alone. Start with the shape of space itself. In the early 1990s, cosmologists realized that space, the actual geometry of the universe, could be measured the same way you would measure the geometry of a triangle drawn on paper or on the curved surface of a ball. Draw a triangle on a flat sheet, and its three angles always add up to 180 degrees, no more, no less. Draw that same triangle on the surface of a sphere, and the angles add up to more than that, because the surface itself is curved back on itself. Draw a triangle on a saddle-shaped surface, and the angles add up to less. Space, real physical space, behaves the same way. It has a shape, and that shape can be measured. The measurement comes from light that has been traveling since the universe was about 380,000 years old. A faint bath of radiation called the cosmic microwave background. Frozen into that radiation are tiny patterns, ripples left over from the first structures that ever formed. The size of those ripples, compared to how far away they are, tells us whether the space they traveled through bent the light inward, outward, or left it alone. Satellites built for exactly this purpose have measured the answer with extraordinary precision. Space, on the largest scales we can observe, is flat. Not almost flat in some loose sense, but flat to within about 0.4%, which is close enough that some cosmologists think perfectly flat is not just a good approximation but the literal truth. This was not one measurement made once and trusted blindly. 3 separate generations of spacecraft, one in the late 1980s and early 90s, another in the early 2000s, and a third launched in 2009. Each mapped that same afterglow with better instruments than the one before, and each one returned the same answer, refining it rather than overturning it. That kind of repeated confirmation across missions built decades apart by different teams using different technology is what gives cosmologists confidence that the flatness of space is not a fluke of one instrument, but a real property of the universe we live in. A flat universe is not the same as a small one. If space curves back on itself, like the surface of a sphere, then in principle it can be finite even while having no edge, the way you could walk in a straight line on the surface of a planet and eventually return to where you started without ever hitting a wall. But flat space, as far as the mathematics is concerned, does not fold back on itself. It does not loop. Unless something very strange is happening on scales far larger than what any telescope has ever seen, a flat universe simply keeps going, in every direction, without end. This is the detail most people miss when they picture the cosmos. The part we can see, the observable universe, is a sphere roughly 93 billion light-years across, containing something like 2 trillion galaxies, each one home to, on average, around 100 billion stars. That number is already difficult to hold on to. But the observable universe is not the whole universe. It is only the part close enough that its light has had time to reach us since the universe began, about 13.8 billion years ago. Beyond that boundary, space in all likelihood continues. We simply cannot see it, because its light has not arrived yet, and given how fast space itself is stretching, some of it never will. So the honest picture that comes out of decades of careful measurement looks like this. Our little sphere of 2 trillion galaxies is a rounding error inside, something that may have no edge at all. And once you accept that the space beyond our horizon probably looks, on average, like the space we can see, filled with the same kinds of galaxies, obeying the same laws of physics, something uncomfortable follows almost automatically from ordinary probability. If there is only a finite number of ways to arrange the matter inside a region the size of our observable universe, and if that same kind of region repeats itself without end, across a universe with no boundary, then every one of those finite arrangements must eventually repeat. Not most of them. All of them. It helps to think about this in terms of a single, well-defined patch of space, rather than the universe as a whole. Cosmologists sometimes call a region the size of our observable universe a Hubble volume, a convenient unit for talking about repetition without needing to invoke the entire, possibly endless, universe all at once. Under the reasoning above, a flat and uniform universe should contain a genuinely uncountable number of these Hubble volumes stitched together, one after another, in every direction. Most of them will be filled with matter, arranged in ways nothing like our own corner of space. Ordinary but unfamiliar, galaxies in different positions, stars burning at different ages. But because the number of distinct ways to arrange the matter inside a single Hubble volume is finite, no matter how enormous that number is, an unlimited supply of Hubble volumes guarantees that the specific arrangement making up our own gets repeated, not once, but endlessly, spaced out across a distance too large for any signal to ever cross. Here is why that arithmetic actually works. A region of space, the size of what we can observe, contains a huge but countable number of particles, something on the order of 10 to the power of 80 atoms. Each of those particles can only exist in a limited number of physical states, positions, energies, spins, and so on, once you account for the rules of quantum mechanics. Physicists who work through the bookkeeping on this arrive at an estimate for the total number of distinct ways a region that size could possibly be arranged: matter, energy, radiation, all of it. And the number they land on is somewhere around 10, raised to the power of 10 to the power of 118. Written out in full, that is, a 1, followed by so many zeros that if you tried to write 1 0 per atom in the observable universe, you would run out of atoms long before you ran out of zeros. This kind of counting is not unique to cosmology. Physicists working on black holes discovered decades ago that any finite region of space, once you account for both matter and energy, has an upper limit on how much information it can contain, tied to the size of its boundary rather than its volume, a genuinely counterintuitive result that first emerged from studying how black holes swallow information and slowly leak it back out as faint radiation. It means a region shaped like a sphere cannot store more distinct configurations than a number set by the area of its outer surface, measured in fundamental units far smaller than an atom, no matter how densely you try to pack matter into the space inside. This limit, sometimes called the holographic bound, has held up under every theoretical test physicists have thrown at it since. And it is the same kind of reasoning that lets researchers put a genuine, finite number on how many ways a region the size of our observable universe could possibly be arranged, rather than simply throwing up their hands and calling it uncountable. That limit means a region of space cannot hold infinite detail, no matter how finely you try to divide it up. Apply that same limit to a region the size of our observable universe, and the result is the almost incomprehensible but still finite number of possible arrangements mentioned above. The finiteness is not a guess. It falls directly out of combining quantum mechanics with the physics of information, two of the most thoroughly tested frameworks science has ever produced. That number sounds unimaginably large, and it is. But large is not infinite, and a universe with no edge has room for a number that size to repeat over and over without limit. The physicist Max Tegmark worked through this calculation directly and arrived at a distance, an actual number of meters you would need to travel before running into an exact copy of our observable universe, atom for atom, star for star, and person for person. The distance is so large that comparing it to anything familiar does not help. It dwarfs the size of the observable universe itself by a margin that would take more digits to write than there are particles in everything we can see. But it is a finite distance. Under this reasoning, it is not a metaphor to say that another version of everything happening in this room right now exists somewhere out there. It is closer to an unavoidable conclusion of the mathematics, provided the two assumptions behind it hold. That space truly goes on without limit, and that the same average density of matter continues out there the way it does here. It is worth sitting with what identical actually has to mean in this calculation, because it is a much stricter word than it sounds. This is not a planet that merely resembles Earth, with similar oceans and a similar sky. It is a region where the quantum state of every particle, down to the exact configuration of every atom inside every brain, matches ours precisely, which means a person there would be having, at this instant, the same electrical patterns firing across the same neural pathways, produced by the same arrangement of matter, arriving at the same thought, in the same order, for the same reasons. Between here and there lies an amount of ordinary, unremarkable space filled with its own galaxies, its own stars, its own version of everything cosmology has ever catalogued. None of it especially unusual on its own, simply arranged differently than the small patch we happen to occupy. Over and over, for a stretch of distance that no spacecraft, no signal, and no beam of light will ever finish crossing. Nothing about the calculation requires that region to be reachable, or observable, or connected to us in any way beyond sharing the same physical laws and enough empty space in between. Distance, in an unbounded universe, does not prevent existence. It only prevents contact. Both of those assumptions deserve to be questioned, and a responsible telling of this idea has to include what we do not actually know. The flatness measurement comes with a margin of error, and a universe that curves back on itself just slightly, too gently for current instruments to detect, remains entirely possible. If that turns out to be the case, the universe could still be enormous while technically closed, folded back on itself the way the surface of a very, very large sphere would look completely flat to anyone standing on a small patch of it, without truly extending forever. There are even more exotic possibilities that some cosmologists have taken seriously, where space is flat locally, but connected to itself in unusual ways, similar to the way an old video game screen wraps a character back around to the opposite edge when they walk off one side, producing a universe that is finite in total volume while still having no boundary or edge that anyone could ever physically reach. None of these alternatives have been ruled out. What has been ruled out, fairly firmly, is any strong curvature on the scales we can measure, which narrows the honest possibilities down to somewhere between very large and truly endless, without settling the question completely. There is also a subtler assumption buried inside the whole argument, one easy to miss. The claim that every possible arrangement of matter must eventually repeat depends on space being filled with roughly the same average density of matter everywhere, all the way out. It is conceivable, though most cosmologists consider it unlikely, given how uniform everything we can measure appears to be, that our particular region is in some sense unusual, a denser or more structured pocket sitting inside a much emptier surrounding space. If that were true, the argument for repeated copies would weaken considerably, because the guarantee of repetition depends on matter continuing at a consistent density rather than thinning out into emptiness beyond what we can see. But notice what this version of the multiverse does not require. It does not require new particles, new dimensions, or any physics beyond what has already been tested in laboratories and confirmed by satellites. It only requires that the universe is larger than the part we can see, and that far away, the same rules still apply. Most working cosmologists consider both of those things likely, which means the most conservative reading of modern physics, the version that assumes nothing exotic, still leaves room for another version of this exact moment, happening somewhere completely out of reach. It is worth pausing on why physicists trust that the universe keeps behaving the same way beyond what we can see, because the whole argument depends on it. Every direction we point a telescope, once we average over large enough distances, roughly 300 million light-years or more, the universe looks the same. The same density of galaxies. The same mix of hydrogen and helium left over from the earliest minutes after the Big Bang. The same background temperature to within a few hundred thousandths of a degree in every direction we check. This uniformity has a name, the cosmological principle, and it is not an assumption made out of convenience. It is a pattern confirmed by every large-scale survey ever conducted. If the universe looked different in different directions, if one patch of sky showed galaxies piling up while another showed nothing but empty space, the whole argument about repeating patterns would fall apart, because there would be no reason to think the far side of the universe behaves anything like our side. Large galaxy surveys, projects that have spent decades mapping the positions of millions of galaxies across enormous stretches of the sky, show exactly this kind of consistency. One such survey, running for more than 2 decades from a dedicated telescope in New Mexico, cataloged the precise positions and distances of well over 1 million galaxies and quasars, building a 3-dimensional map of the universe, accurate enough to measure subtle patterns left over from sound waves that rippled through the early universe before the first stars ever formed. Other surveys, run from different continents using entirely different instruments, have independently confirmed the same broad picture. Zoom in, and the universe looks intricate and clumped, galaxies gathered into clusters, clusters strung along filaments, with vast, nearly empty voids stretched between them, a structure astronomers sometimes call the cosmic web. Zoom out far enough, past the scale of any individual filament or void, and that intricate structure smooths out into the same average density, no matter which direction you look. It is the same pattern you would expect if you photographed a single square centimeter of a forest up close. Seeing individual leaves and branches in fine detail, then photographed the entire forest from an airplane and saw only an even, undifferentiated green. But that is not what the data shows at the largest scales measured. Every test says the universe is smooth on the largest scales, and smooth in a way that has no obvious edge or center. Extending that smoothness past our cosmic horizon is an extrapolation, and honest scientists call it exactly that. But it is an extrapolation built on evidence stretching in every direction we have ever looked, not a guess pulled from nowhere. There is a deeper reason to expect the universe to be even larger than the flatness measurement alone suggests. And it comes from a chapter of cosmic history that lasted an almost unimaginably short amount of time. In the first sliver of a second after the Big Bang, before the universe was even a trillionth of a second old, most cosmologists believe space underwent a burst of expansion, unlike anything that happened afterward. Not fast expansion in the ordinary sense, but doubling expansion, where the size of space doubled, then doubled again, then again, over and over in a span of time too short for a single atom to complete one full quantum vibration. This period is called inflation, and it solves several problems that had puzzled cosmologists for decades, including why the universe looks so flat and so uniform in every direction in the first place. Cosmologists were not looking for a strange idea when inflation was first proposed in the early 1980s. They were trying to solve a specific, nagging problem. Regions of the sky on opposite sides of us, so far apart that light from one side could never have had time to reach the other since the Big Bang, show almost exactly the same temperature in the cosmic microwave background, to within a few hundred thousandths of a degree. Without some mechanism to explain it, there is no obvious reason distant, disconnected regions should have settled into such a close match, the way two rooms with no shared heating system should not end up at the exact same temperature by coincidence. A short burst of extremely rapid early expansion solves this cleanly, because it means those regions were in close contact before inflation stretched them apart, giving them time to reach the same temperature first. The same burst also explains the flatness we already discussed, by stretching out whatever curvature the universe started with until it became undetectably small. The way inflating a balloon to an enormous size makes its surface look locally flat to anyone standing on it. Inflation solves several genuine puzzles about the shape and uniformity of the universe that nothing else explains as cleanly. And it does so because once that kind of runaway doubling begins, stopping it everywhere at once turns out to be far harder than starting it in the first place. The same sensitivity to tiny disturbance mentioned earlier, the kind that lets small atmospheric differences steer entire weather systems onto different paths, applies here as well. Only acting on the field, driving inflation itself rather than air and moisture, nudging some patches toward ending sooner and others toward continuing far longer than average. Inflation is driven by a field of energy that physicists call the inflaton, and the way that field behaves has a strange consequence. In most places, the field settles down quickly, inflation ends, and an ordinary Big Bang begins, cooling and forming stars and galaxies the way ours did. But quantum fluctuations mean that in some patches, instead of settling down, the field gets nudged upward, and inflation keeps going, even accelerates. The regions where inflation ends become isolated pockets, each one its own Big Bang, each one growing into its own vast stretch of space. The regions where inflation continues keep producing more pockets endlessly, because the process that ends inflation locally never manages to end it everywhere at once. This is called eternal inflation. And under this picture, our entire observable universe, everything we have ever measured, the 93 billion light-year sphere and whatever ordinary space lies beyond it, is just one pocket inside a churning, endless sea of expanding space that is constantly spinning off new pockets elsewhere. It helps to picture something like a pot of water kept just at the point of boiling, where bubbles constantly form, grow, and detach from the bulk of the liquid around them. Except in this picture, the boiling itself never runs out of water to work with, because the space between the bubbles keeps stretching and expanding faster than any single bubble could ever fill it. Each detached bubble becomes its own pocket universe, cooling and settling into ordinary physics inside, while the churning space between bubbles continues forever, producing new ones without any indication of slowing down. Some of those other pockets, if the deeper mathematics of particle physics is right, could end up with completely different physical constants, a different strength of gravity, a different mass for the particles that make up atoms, even a different number of usable dimensions. Most such pockets would likely be hostile to anything resembling chemistry, let alone stars or life. But among the enormous number of pockets that do end up with physics close to ours, the same argument about finite arrangements repeating across infinite space applies all over again, just one level further out. The differences between these pockets are not expected to be small. In one leading candidate for a deeper theory of physics, string theory, extra dimensions of space, curled up far too small for any instrument to detect, can be folded in an enormous number of distinct geometric ways. And each distinct folding corresponds to a different set of effective laws in the pocket universe that results. These extra dimensions, in the mathematics, are not simply extra directions to move in, but tightly wound geometric shapes, complex enough that describing just one of them in full detail can take mathematicians' entire careers, folded so small that their effects only show up indirectly through the exact masses and behaviors of the particles that physics is built from. A different folding produces a different particle, a different force strength, sometimes an entirely different number of forces altogether. Researchers refer to this vast catalog of possible foldings as the landscape, and current estimates for how many distinct versions it might contain run past 10, multiplied by itself 500 times, a number so far beyond ordinary counting that physicists usually just write it as an exponent and move on. The clearest example of this fine-tuning puzzle involves the energy woven into empty space itself. The same energy responsible for the accelerating expansion astronomers discovered by watching distant exploding stars in the late 1990s. Calculations from particle physics, run the ordinary way, predict that this energy should be enormous, dozens of orders of magnitude larger than what telescopes actually measure. The observed value is not merely smaller, it is smaller by a factor large enough that most physicists consider it one of the strangest, unexplained numbers in all of science. If that value had come out only modestly larger than it did, the expansion of space would have overwhelmed gravity before galaxies ever had a chance to pull themselves together, and nothing like a star, a planet, or an observer capable of measuring any of this would ever have formed. A landscape of countless pockets, each with a different value for this same quantity, turns an apparently absurd coincidence into something closer to a filtered sample. We could only ever find ourselves measuring a value gentle enough to allow galaxies, because no observer could exist to measure any of the far more common, harsher alternatives. Push the strength of the force-binding atomic nuclei together up or down by only a small fraction, and protons and neutrons stop forming anything past the very lightest elements, leaving a pocket with nothing heavier than hydrogen and no path toward chemistry, planets, or stars that burn the way ours does. Shift the mass of the electron by a similar margin, and atoms stop holding together the way they need to for molecules of any complexity to form. Only a narrow slice of that landscape would allow anything resembling stable atoms, let alone stars, planets, or chemistry complex enough to support life. This is where a genuinely useful piece of reasoning called the anthropic principle comes in. It notes, almost trivially once stated, that any observer capable of measuring the laws of physics must exist inside a pocket universe whose laws permit observers to exist. This explains something that has puzzled physicists for a long time: why several of the fundamental constants of nature, the strength with which empty space pushes outward, for instance, sit at values that seem almost absurdly well suited for galaxies and stars to form, when simple calculations suggest almost any other value would have prevented complex structure from ever appearing. If countless pockets exist with countless different values, then finding ourselves in one of the rare pockets compatible with our own existence stops being a coincidence in need of a special explanation. It becomes the only kind of pocket any observer could ever find themselves measuring from. Not every physicist finds this style of reasoning satisfying, and the objection is worth stating plainly rather than glossing over. Critics point out that explaining why we observe life-permitting values by saying only life-permitting values could ever be observed risks becoming true, no matter what the underlying physics turns out to be. which makes it difficult to use as a genuine test of any specific theory. If the landscape were entirely different, the same style of argument could just as easily explain whatever different values happen to show up, which is exactly the kind of flexibility that makes some scientists uneasy, since a genuinely useful scientific explanation should, in principle, be capable of being wrong. Supporters of the reasoning respond that it is not meant to replace an underlying physical explanation, only to correct a mistaken expectation, the mistaken expectation that we should be surprised to find ourselves in a life-permitting universe, when in fact, no other kind of universe could ever have anyone in it to be surprised. Both points are reasonable, and the disagreement between them remains active in the scientific literature rather than settled. A handful of physicists have gone further still, proposing that black holes themselves might act as seeds for entirely new expanding regions of space on the other side of their collapse. A genuinely speculative idea, sometimes called cosmological natural selection, suggesting that universes producing more black holes might, in some sense, produce more descendant universes over time. This particular proposal remains a minority position even among physicists who take the broader multiverse seriously, and it has not gained the same level of support as eternal inflation. It is worth mentioning only to show how many genuinely different routes serious researchers have explored toward the same general destination, a universe that produces more of itself rather than existing as a single, isolated occurrence. None of this can be observed directly, and it may never be. The other pockets, if they exist, lie beyond a boundary that is expanding faster than light could ever cross it, which is not a violation of physics, just a consequence of what inflation does to space itself. But the theory that predicts this endless production of universes is the same theory that correctly predicted the fine details we do measure in the afterglow of our own Big Bang, tested and confirmed by spacecraft built specifically to check it. That does not prove eternal inflation is true. It means the idea did not come from speculation. It came from taking a well-tested theory seriously and following its equations to where they lead. To get a feel for how much detail actually has to line up for a distant twin to count as identical, it helps to consider just how much information a single human brain carries. A typical brain contains something like 86 billion neurons, connected to each other through roughly 100 trillion individual synapses, each one capable of varying in strength, depending on a lifetime of chemical signaling. Estimates for the raw storage capacity implied by that structure run into the range of several petabytes, a unit normally reserved for describing entire data centers rather than a single organ carried around inside a skull. For a distant region of space to count as containing a genuine twin, every one of those trillions of synaptic connections, along with the exact chemical state of every neuron and every supporting cell around it, would need to match, not approximately, but down to the same physical detail responsible for producing this specific thought at this specific moment. That the mathematics of a sufficiently large, sufficiently uniform universe still guarantees this kind of match, however astronomically rare it is, says something about just how large that universe would have to be, and just how seriously the guarantee should be taken once you accept the starting assumptions. It is worth being clear about language here, because the word multiverse gets used loosely enough in casual conversation that it can blur together ideas that are actually quite different from each other. Physicists who study this seriously, following a classification popularized by the same researcher who worked out the distance to a cosmic twin, tend to number these possibilities to keep them straight. A distant twin sitting somewhere far away inside the same single, continuous universe we occupy is usually called the first level, the simplest and most conservative version, resting only on an unbounded universe and consistent physics throughout. Separate pocket universes produced by eternal inflation, each with a genuine chance of carrying different physical constants, form the second level. A branch of the quantum wave function, requiring no distance at all since it happens right here, continuously, is the third level. And the idea that every logically consistent mathematical structure exists as its own physical reality sits at the fourth and most speculative level of that same classification. Keeping these categories distinct matters because they rest on different evidence, carry different levels of confidence, and would be confirmed or ruled out by entirely different kinds of observations. There is a completely different route to the same unsettling place, and this one does not need the universe to be large at all. It comes from quantum mechanics, the theory that governs how atoms, light, and particles behave, and it is the most precisely tested theory in the history of science. Some of its predictions have been checked to an accuracy of about 1 part in a trillion, roughly like measuring the distance between two cities and getting it right down to the width of a human hair. Quantum mechanics describes particles not as having one definite state, but as existing in a mixture of possible states at once, a wave of possibilities, until something interacts with the particle in a way that forces one outcome to show up. Send a single particle of light toward a screen with 2 narrow slits cut into it, and rather than passing through one slit or the other the way a tiny ball would, the mathematics insists it passes through both at once, interfering with itself on the far side to build up a pattern that only makes sense if both possibilities were genuinely explored. This is not a limitation of measurement or a gap in our knowledge waiting to be filled in. Every experiment ever devised to check confirms that the particle really was doing both things, right up until something forced a single outcome to appear. A photon can be spinning one way or another. An unstable atom can decay in the next second or remain intact. Before anyone checks, the mathematics treats both outcomes as equally real, layered on top of each other. The strange part is what the equations say happens next. They do not describe a moment where one possibility wins and the other simply vanishes. Left alone, the equations just keep spreading the possibilities outward, forever, with nothing in the mathematics that ever collapses them down to one. In 1957, a graduate student named Hugh Everett proposed taking that mathematics at face value. If the equations never collapse, he argued, then maybe they never need to. Maybe every time a quantum event could go one of several ways. All of the ways happen, but they happen in branches of reality that stop interacting with each other the instant they diverge. From inside any one branch, it looks exactly like an ordinary outcome occurred, and the others never existed. But according to the mathematics, all of them are equally real, drifting apart from each other permanently the moment they split. Physicists have a famous, deliberately absurd way of dramatizing this same puzzle, imagining a sealed box containing a cat, along with a single radioactive atom wired to release a poison if it decays within the next hour. Treated with strict mathematical honesty, and before anyone opens the box to check, the equations describe the atom as existing in a mixture of having decayed and not having decayed simultaneously, which would seem to leave the cat inside in an equally uncomfortable mixture of two contradictory states at once. The scientist who first proposed this scenario intended it as a criticism, a way of showing how strange the equations become once you stop treating quantum uncertainty as something confined only to tiny particles, and instead let it apply to something the size of an ordinary house pet. Everett's answer to that criticism is that the strangeness never actually goes away, it simply gets relocated. Opening the box does not resolve some hidden contradiction. It is the moment the observer opening the box becomes entangled with the same branching structure the cat and the atom were already part of, splitting into a version who finds a living cat and a version who does not, each one certain, from that point onward, that theirs was the only possible outcome all along. The mechanism that makes branches stop talking to each other has a name: decoherence, and it has actually been observed in laboratories, even though the full-scale branching Everett proposed has not. When a delicate quantum system, a single atom held in careful isolation, comes into contact with its surroundings, even something as ordinary as a stray photon bouncing off it, the interaction spreads the quantum information into the environment so quickly and so thoroughly that the different possibilities can no longer interfere with each other in any way that could ever be measured again. That process is what Everett's picture leans on to explain why branches, once they split, never rejoin. It is not that the other outcome is destroyed. It is that reversing the split would require gathering back every last photon and every last particle that ever interacted with the system, which is not merely difficult, it is beyond what the laws of physics allow once enough time has passed. Everett's idea was mostly ignored for years. It is now taken seriously by a significant number of physicists, not because it is comfortable, but because it removes a problem that every other interpretation of quantum mechanics struggles with: the question of what exactly counts as a measurement and why the universe would treat that moment as special. Everett's version needs no such special moment. It just applies the same equations everywhere, all the time, without exception. There remains a genuine dispute, even among physicists who accept the underlying mathematics, over whether the other branches deserve to be called real, in the same sense the branch you are experiencing is real, or whether they are better described as mathematical bookkeeping, a formal device that correctly predicts what you should expect to observe without requiring every unobserved possibility to carry the same weight of existence as the one actually lived. Everett himself argued for the stronger reading, that the branches are as real as anything physics has ever described. Many of his supporters today hold the same position. Others who work with the same equations daily remain agnostic on that specific philosophical point, treating the formalism as reliable without committing to a firm answer about what, if anything, is actually happening in the branches nobody will ever see. It is only fair to note that many worlds is not the only serious way physicists interpret this same mathematics, and plenty of thoughtful researchers prefer alternatives. One older interpretation simply says that a measurement causes the wave function to collapse down to a single outcome, full stop, without offering a precise physical account of what a measurement is or why it would trigger collapse rather than more branching. A gap critics have pointed out for the better part of a century. Another interpretation keeps a single definite reality at all times by adding an extra, hidden layer of information, guiding each particle along one specific path, at the cost of introducing effects that appear to act instantly across any distance, which sits uneasily next to other parts of physics built around nothing traveling faster than light. Every interpretation of quantum mechanics currently on the table comes with some cost, some assumption that feels uncomfortable once you look closely enough. And many worlds is not immune to that pattern. It simply trades a hidden collapse mechanism for an enormous, continuously multiplying reality most people never directly perceive. Choosing between them, at the moment, is less a matter of settled evidence and more a matter of which discomfort a given physicist finds easier to accept. If this picture is correct, the consequences reach directly into the chemistry of your own brain. Neurons fire because of chemical processes that ultimately depend on quantum events. Every one of those events, at every instant, in every brain, in every living thing, is a branch point. The number of branches produced every second, across all the matter in just one planet, is a number that grows faster than any ordinary description can keep up with. Laboratories have confirmed pieces of this mechanism directly, sending molecules made of hundreds of atoms, far larger than a single particle of light, through the same kind of two-path interference experiments once reserved for individual photons, and watching the delicate interference pattern wash out the moment the surrounding environment gains enough information to, in principle, reveal which path the molecule took. That washing out is decoherence happening in real time, measured on equipment sitting in an actual laboratory, rather than argued about only on a chalkboard. It is held up under every attempt to detect its exact edges, which is precisely why so many physicists treat it as one of the more solid pieces of an otherwise speculative picture. One confirmed physical mechanism, sitting underneath the much larger, much less confirmed claim that entire branches of reality genuinely separate from each other at that same moment. One detail keeps this picture from collapsing into nonsense: the observation that not all branches carry equal weight. Quantum mechanics has always predicted that some outcomes are far more probable than others, and Everett's supporters have spent decades working out how that ordinary sense of probability survives in a picture where every outcome technically happens somewhere. The working answer, still debated in its finer mathematical points, is that branches are not simply counted like objects in a list, but weighted, the way a much larger portion of a pie corresponds to a much likelier outcome, even though every slice, thick or thin, is equally real once it exists. Rare outcomes still happen in some branch, but they happen in a comparatively small sliver of the whole, while common outcomes occupy the overwhelming majority of it. That weighting is exactly what allows quantum mechanics to keep making the same accurate predictions it always has, regardless of whether you believe the other branches exist or not. Which means that under this interpretation, at this very moment, there are branches of reality where you paused this a few seconds ago, branches where you are hearing this while distracted by something else entirely, and branches where a single decision this morning, so small you have already forgotten it, sent you down a path that looks nothing like the one you are actually living. All of them, if Everett is right, are equally real, equally physical, and equally unaware of each other, each one convinced it is the only one that exists. Let that settle for a moment before moving further, because the next idea depends on taking both of the previous ones seriously at once. An enormous or endless universe on one hand, and the strange behavior of quantum systems on the other. Push either of these ideas far enough, and you run into something even stranger, a problem that cosmologists take seriously enough to treat it as a genuine test for whether a theory can be trusted at all. It comes from a 19th century physicist named Ludwig Boltzmann, who showed that disorder tends to increase not because nature is forcing it to, but because disordered arrangements of matter vastly outnumber ordered ones. So ordinary random motion is simply more likely to wander toward disorder than away from it. Given enough time, though, the reverse can happen too. Left alone for long enough, in a large enough space, random motion can, purely by chance, assemble something ordered out of chaos, the way a room full of gas molecules could, in principle, briefly clump together into a recognizable shape, if you were willing to wait far longer than the current age of the universe many times over. Now, stretch that waiting time out to the scale that eternal inflation or an endless universe implies, and something troubling shows up. If space and time genuinely go on without limit, then somewhere, eventually, random fluctuations in an otherwise cold and empty stretch of the far future universe will assemble a functioning brain, complete with false memories of a life it never lived, a body it does not have, and a universe around it that ended the moment after it appeared. This thought experiment is called a Boltzmann brain, and it exists as a warning sign rather than a serious prediction about your own existence. If a cosmological model implies that these randomly assembled, momentary brains vastly outnumber brains that develop the ordinary way, through billions of years of biological evolution inside a coherent universe, then that model has a serious problem, because it would suggest that the most likely explanation for any given conscious experience is a fleeting accident rather than a real, continuous history. Most physicists take this as evidence against certain versions of eternal inflation, not evidence that you personally are a fluctuation. There is a simple, practical reason for that confidence beyond the entropy argument already described. A randomly assembled brain would have no reason to come with memories that cohere into a consistent, checkable history. Memories of physics experiments that agree with other people's memories of the same experiments, memories of a childhood that other people who were present can independently confirm. A fluctuation is, statistically, always more likely to produce a much smaller, much simpler illusion than an entire elaborate history that lines up perfectly with billions of other people's independent records. The fact that your memories check out against a shared, external, physical record, other people, old photographs, geological layers, starlight from events that predate any human witness, is itself strong practical evidence that this particular observer is not one of the sparse, isolated fluctuations the thought experiment describes. The setting where this problem actually bites is the far future of our own universe. Long after anything resembling the sky you could step outside and look at tonight has changed beyond recognition. Stars form from hydrogen, a fuel supply that is finite, and current estimates suggest the last ordinary stars will finish burning somewhere around 100 trillion years from now. A span of time roughly 7,000 times longer than the universe has existed up to this point. After that comes a long, dim stretch, dominated by the slow cooling of dense stellar remnants, followed by an era where black holes are the largest structures left, and even they do not last forever. Left alone, a black hole slowly radiates its mass away as faint radiation, a process so slow that for the largest black holes, it would take something on the order of 10 multiplied by itself 100 times in years before the last one finally evaporates. It is in the almost incomprehensibly long, cold, empty stretch after that point where random fluctuations would have enough time and enough room to occasionally assemble something as complex as a functioning brain out of sheer chance. There is a subtler layer to this problem that professional cosmologists actually use as a working tool, sometimes called typicality reasoning. The basic idea is that if a theory predicts you should expect to be an unusual kind of observer, a fluctuation floating alone in an empty universe rather than a creature embedded in a long, structured cosmic history, and yet you clearly are not that kind of observer, then the theory predicting otherwise has a genuine problem, regardless of how elegant its other features might be. This kind of reasoning sits inside a broader philosophical toolkit, sometimes called the self-sampling assumption, the idea that, in the absence of other information, a given observer should reason as though they were a randomly selected member of whatever larger group of observers actually exists. Applied honestly, that assumption becomes a genuine constraint on cosmological models, since a model predicting that the overwhelming majority of observers should be brief, isolated, memory-laden fluctuations, rather than observers, embedded in long structured histories, is a model making a testable claim about what a typical observer should expect to find, and that claim can be checked against what we actually do find. This is not mysticism. It is closer to a sanity check, the same kind of reasoning a scientist would apply if a model of loaded dice predicted that rolling a specific rare number should happen constantly, while ordinary rolls almost never occurred. And then an honest, ordinary series of roles kept coming up perfectly normal. Something in the model would need revisiting. Applied to cosmology, this kind of typicality check has actually ruled out certain versions of eternal inflation that predicted an overwhelming majority of observers should be exactly the kind of randomly assembled, short-lived fluctuation described above, since our own observed universe, with its long, orderly, low-disorder history stretching back 13.8 billion years, is exactly the wrong shape for that kind of accidental origin. The universe you and I are embedded in has consistent history stretching back billions of years, confirmed by geology, by starlight, by the careful layering of matter that a random fluctuation could never produce all at once. But the fact that serious researchers have to check their models against this possibility says something about how seriously the implications of infinite space and infinite time are taken. When you allow enough time and enough room, the line between what is likely and what is merely possible starts to blur in ways that ordinary intuition was never built to handle. It is worth pausing here, because three genuinely different arguments have now pointed toward the same uncomfortable place, and it matters that they arrived there independently. One argument came from measuring the geometry of space itself and combining that measurement with ordinary probability. A second came from taking the standard theory of the earliest fraction of a second after the Big Bang and following its equations without editing them to feel more comfortable. A third came from taking the best tested theory in physics, quantum mechanics, and refusing to add an extra, unexplained rule about when reality is supposed to collapse down to one outcome. None of these three arguments were built to support each other. They came from separate branches of physics, studied by different researchers, decades apart, using different mathematics entirely. That they all lead towards some version of repetition, whether across space, across separate pockets of inflation, or across branching quantum outcomes, is not proof that any one of them is correct. But it is a pattern worth noticing, the kind of pattern that, in the history of physics, has often turned out to be pointing at something real. There is one more step that some physicists are willing to take, and it is worth mentioning, even though it moves further from settled science than anything discussed so far. Throughout the history of physics, every deeper theory has turned out to be, at its core, a mathematical structure. Not a description of physical stuff that happens to obey mathematical rules, but a set of equations that appears to be the actual bedrock of what is happening. This has led a small number of researchers, most notably Max Tegmark again, to propose something called the mathematical universe hypothesis. The idea that every mathematical structure which is logically consistent corresponds to a genuinely existing universe, not as a metaphor, but as a physical fact. Under this idea, our universe is not special because it has a particular set of equations. It is one of an enormous, perhaps unlimited, collection of mathematical structures, and we happen to exist in this one because this is one of the structures complex enough to contain something capable of noticing itself. A physicist named Eugene Wigner wrote an essay in the 1960s pointing out something genuinely strange, that equations invented by mathematicians for their own internal elegance, with no physical application in mind at all, keep turning out decades or centuries later to describe real physical phenomena with startling accuracy, as though the universe were somehow already written in a language mathematicians had been exploring blindly and for its own sake. He called it the unreasonable effectiveness of mathematics, and the puzzle he raised has never been fully resolved. Why should abstract symbol manipulation, done purely for its own logical satisfaction, map so precisely onto how light bends, how particles decay, how galaxies rotate? The mathematical universe hypothesis is, in part, an attempt to dissolve that puzzle entirely, by proposing that there was never a gap to bridge in the first place, because physical reality and mathematical structure were the same thing all along. This is the most speculative version of everything discussed tonight, and many physicists are openly skeptical of it, partly because it is difficult to see how it could ever be tested. But it does answer, in a strange way, a question that has bothered physicists for a long time: why mathematics describes nature so well in the first place. If existence and mathematical consistency are the same thing, the answer stops being a mystery and starts being close to a definition. All of this eventually forces a question that physics alone cannot answer, and it is worth sitting with honestly rather than rushing past. If another arrangement of atoms, somewhere unreachable, is having the exact same thoughts you are having right now, is that arrangement you, or is it simply someone else who happens to be identical to you? The question sounds like a word game, but it points at something real. Because most of us carry an unspoken assumption that there is exactly one continuous thread running through our life. A single self that started somewhere and has been quietly persisting ever since. Ancient philosophers had a name for this puzzle long before biology could explain how bodies actually replace themselves: the ship of Theseus. A thought experiment about a wooden ship kept in repair for so many years that every single plank eventually gets swapped out for a new one piece at a time, until nothing of the original material remains, while sailors and townspeople alike keep calling it the same ship the entire time. Human biology runs a quieter version of the same replacement constantly. The lining of your stomach renews itself within about a week. Red blood cells last only a few months before being replaced. Even bone, which feels as permanent as anything in the body, is fully rebuilt over a span of roughly a decade. The brain is more conservative. Many neurons persist for a lifetime, but the molecules making up those neurons, and the trillions of connections between them, are in constant chemical flux, strengthened, weakened, pruned, and rebuilt continuously in response to everything you experience. Memory, the part of you that feels most like a permanent record, turns out to be the least permanent of all. Neuroscientists studying how memories are stored have found that recalling a memory is not like pulling a filed document from a drawer. It is closer to reconstructing the memory from scratch each time, using fragments stored across different regions of the brain, reassembled slightly differently depending on your current mood, your more recent experiences, and what you have learned since the event happened. This is why two people who witness the exact same moment often remember it in genuinely different, sometimes contradictory ways years later. Not because either one is lying, but because both memories were rebuilt rather than replayed. If the thing most people point to as the seed of their unbroken identity is itself being quietly rewritten every time it is used, the idea of a single unchanging thread running through a life starts to look less like an observed fact and more like a comfortable simplification. What actually persists, across all of this constant replacement, is not a fixed material thing, but a pattern, a process that keeps enough continuity from one moment to the next that calling it the same person remains useful, without there needing to be some separate essence underneath the pattern that makes it truly, metaphysically singular. The philosopher Derek Parfit spent much of his career pushing on exactly this question, using thought experiments built around teleportation and gradual replacement to show that the sharp line most people imagine between me and someone else who is exactly like me does not hold up under pressure. If a machine could scan every atom in your body, then assemble an identical copy somewhere else out of new material while the original was taken apart, most people's first instinct is to say the person who steps out the other side is a copy, not a continuation. But pressed further, it becomes difficult to say exactly what was lost in the process. If the resulting person has every memory, every intention, every trace of personality intact. Parfit's conclusion, one that unsettled a great many readers when he first published it, was that personal identity is not the deep, unbreakable fact people assume it to be. It behaves more like a useful story, one that helps a mind organize its own experience, rather than a hard boundary written into the structure of reality. It is also worth noticing that the word twin, borrowed here for convenience, carries its own misleading baggage. Ordinary twins share a great deal: appearance, sometimes temperament, often a great deal of shared history, but they are still, by any reasonable definition, two separate people, with two separate streams of experience from the moment they are born. What tonight's argument describes is stricter than that in one direction and looser in another. Stricter, because it requires a match down to the last atom rather than a family resemblance. Looser, because unlike ordinary twins, this distant counterpart shares no birth, no shared history, no common origin beyond the same laws of physics happening to produce the same result twice, independently, in two places separated by more distance than any twin, in the ordinary sense of the word, has ever had to travel. There is a smaller, more familiar version of this same splitting that everyone has already lived through many times, even without any physics attached to it. The version of you that existed 10 years ago made a choice at some ordinary fork, a job accepted or declined, a move made or not made, a conversation that went one way instead of another, and from that fork, the version of you sitting here now is only one of the paths that could have followed. The version who took the other path is not floating somewhere in branching quantum reality, at least not in any way this argument requires. But the shape of the thought experiment is not unfamiliar, because ordinary memory already holds a faint, private sense of the person you might otherwise have become. What tonight's physics adds is not the concept of a road not taken, which every reflective person already carries privately. It adds the far stranger claim that the road not taken might, somewhere, actually still be walked by someone. Imagine, for a moment, if it were somehow possible to stand in the same room as this distant twin, an impossible scenario given the distances involved, but useful for testing intuition. What would there actually be to say to someone who has lived, atom for atom, the same life you have? There would be nothing to learn from them that you do not already know, since every experience shaping them shaped you in exactly the same way. There would be no advice to offer, no warning to give, no piece of wisdom one version could hand the other that the other did not already, independently, arrive at on their own. The encounter, if it could somehow happen, would resemble looking into an unusually cooperative mirror far more than it would resemble meeting another person, which is perhaps the clearest illustration of just how strange the word identical actually is, once it is taken all the way to its logical conclusion, rather than used loosely the way it gets used to describe twins who merely look alike. A related thought experiment sharpens this further. Imagine a device that could, in principle, scan every particle in your body down to the last detail, transmit that information somewhere else, and reconstruct you there out of entirely new material, while the original body was gently disassembled in the process. Most people asked to imagine stepping into such a device hesitate, sensing that something important might be lost, even if the person who arrives on the other end remembers everything, feels like themselves, and would insist, quite sincerely, that nothing happened to them at all. What exactly would be lost is difficult to pin down, because every physical detail carries over intact. Some philosophers argue that what troubles us here is not really about physics at all, but about an intuition that consciousness must be tied to one continuous, uninterrupted thread of experience, a thread that talk of scanning and reconstruction seems to sever, even when every measurable property of the mind survives the trip. That intuition brushes up against one of the genuinely unresolved questions in modern science, sometimes called the hard problem of consciousness. The question of why physical processes in a brain are accompanied by any inner experience at all, rather than simply happening in the dark, unfelt, the way a calculator processes numbers without anything. It is like to be a calculator. Nobody currently has a satisfying answer. Which means that when we ask whether a distant atom-for-atom identical version of you would have an inner experience exactly like yours, we are really asking a question that sits downstream of a mystery science has not yet solved, a mystery worth naming honestly rather than smoothing over with confidence the field does not actually have. Seen this way, the question is my distant twin me starts to look like the wrong kind of question. The way asking whether two identical printed copies of the same photograph are the same photograph depends entirely on what you mean by the same. In one sense, yes, same image, same details, same story told by the picture. In another sense, no, different sheets of paper occupying different places. Both answers are correct. Neither one is more true than the other. Long before any of this cosmology existed, several schools of ancient philosophy arrived at a related conclusion through entirely different means, simply by paying close attention to lived experience rather than equations. They noticed that the self people cling to so tightly, the fixed, unchanging me that feels like the center of everything, does not hold up well under close examination. Since the body changes constantly, the mind changes constantly, and the only thing that seems to persist is a habit of narrating experience as though a single, stable character were having it. Their proposed remedy was not to deny that a person exists, but to hold identity a little more loosely, identifying less with this one particular instance and more with the ongoing capacity for attention, reason, and care that any instance of a mind, wherever it occurs, is capable of expressing. Physics did not need to agree with that older intuition to end up describing something remarkably similar. A universe where the pattern is what matters, and the specific material carrying it is, in the end, replaceable. The distant version of you, built from the same arrangement of matter, is you in every sense that physics can measure, and is a separate, independent instance of you in every sense that matters for lived experience, because that version will never know you exist, and you will never know anything about their life, their choices, or how their morning went. Picture something as small as a single radioactive atom sitting in a detector, wired so that if it decays within the next minute, a small hammer swings and a bell rings, and if it does not decay, nothing happens at all. Quantum mechanics genuinely does not specify, ahead of time, which of those two things the atom will do. Both possibilities are carried forward by the mathematics right up until the moment of decay or non-decay becomes fixed. Under Everett's reading, both outcomes actually occur, but they occur in branches that no longer share any way of comparing notes afterward. The bell ringing in one, silence in the other, each branch continuing on as though it had always been the only possibility. Multiply that single atom by every comparable event happening inside every brain, every star, and every grain of sand across the observable universe, continuously, and the picture becomes one of a reality, less like a single unfolding story and more like an unfathomably large tree, growing new branches out of every twig, forever, with each new branch fully convinced it is the only trunk that ever existed. This naturally leads to a worry that comes up almost immediately once people hear about branching realities, and it deserves a direct answer rather than a dodge. If every possible outcome of a decision happens somewhere, in some branch or some distant region of space, does the decision itself still matter? It can feel, at first, like choice becomes hollow, since the good outcome and the bad outcome both occur regardless of what you pick, just in different places. But that reasoning skips over something important. You are not a neutral observer, standing outside all the branches deciding which one to watch. You are, at this exact moment, in the process of becoming one particular branch and not the others. The version of you who thinks carefully before acting produces a branch shaped by that care. The version who acts carelessly produces a different branch shaped by that carelessness. Both branches may be real, somewhere in the largest sense the mathematics allows, but only one of them is the one you are actually about to live inside. Moment by moment, with consequences that will feel entirely real to you, regardless of what happens anywhere else. The existence of other branches does not remove the weight of the choice in front of you. It just means the weight of that choice is local to your own thread of experience, rather than a fact about the entire structure of reality. This has a direct bearing on how much sense it makes to hold anyone, including yourself, morally responsible for anything, a question that follows naturally once outcomes start branching. If every possible reaction to a hard moment gets lived out somewhere, does praise or blame still land anywhere meaningful? It still does, for the same reason a judge's verdict still matters, even though a defendant could, counterfactually, have acted differently. Responsibility was never really about whether an alternative was cosmically prevented from happening somewhere else. It was always about whether the specific choice made, here, in this branch, flowed from the reasoning and character of the person making it. That standard does not require the alternative to have been impossible everywhere. It only requires that the actual choice, in the one branch you are answerable for, was genuinely yours. There is an older version of this same worry that has nothing to do with branching universes at all, and it is worth remembering that it predates any of tonight's physics by centuries. Philosophers have long asked whether choices made inside a universe, governed entirely by cause and effect, can be called free in any meaningful sense, since every decision, traced back far enough, rests on prior causes that were never chosen either, a chain of causes stretching back further than any single life. Quantum mechanics was once hoped to rescue free will from that problem by introducing genuine randomness into physics. But randomness is not the same thing as freedom. A choice made by the flip of a truly random coin is not more yours than a choice made by strict cause and effect. It is simply unpredictable rather than free. What philosophers who work on this tend to settle on instead is a more modest, more useful definition that a choice counts as free enough when it flows from your own reasoning, your own values, and your own deliberation, without being forced by something external, regardless of whether the underlying physics is strictly determined, randomly quantum, or endlessly branching. That kind of freedom, the freedom of acting from your own considered reasons rather than someone else's compulsion, survives every version of physics discussed tonight completely intact. That is not a smaller kind of meaning. It is simply the only kind of meaning that was ever available to any of us, in any version of physics, branching or otherwise. It might help, at this point, to notice how strange the ordinary word you actually is once it gets pointed at something this slippery. In everyday use, the word does a great deal of quiet work, gathering together a body, a history, a set of memories, a bundle of preferences and habits, and treating all of it as though it obviously referred to one single, continuous thing. Nothing discussed tonight requires abandoning that word or the convenience it provides. It only asks that the word be understood for what it actually is, a useful label for an ongoing pattern rather than a name for some separate, indivisible essence hiding underneath the pattern, waiting to be found. Once the word is understood that way, A distant twin built from the same pattern is neither a threat to the word nor a loophole in it. It is simply another instance of exactly what the word was always describing. There is a harder version of this same worry worth naming directly. If branching or distant repetition is real, then somewhere a version of you exists who handled every difficult moment with more patience than you managed, who said the kinder thing instead of the sharper one, who kept the harder promise. And somewhere else, a version exists who did the opposite, who gave in to every worst impulse a person is capable of. Neither of those facts, if they are facts, reaches back into this branch to change anything about the choice sitting in front of you right now. The better version cannot lend you their patience. The worse version does not make your own failures any less yours to answer for. Whatever is happening elsewhere, in an unreachable stretch of space, or an already separated branch of the wave function, has no bearing on the only decision you actually have any power over, which is the next one. It is worth being precise about how solid each layer of this actually is, because they are not all equally certain, and pretending otherwise would be dishonest. That the universe is at least as large as what we can observe, roughly 93 billion light-years across and 13.8 billion years in age, is about as well confirmed as anything in cosmology gets. That space appears flat to within a small fraction of 1% is a direct measurement, repeated by multiple independent spacecraft and telescopes. That flat, uniform space extends without limit beyond our horizon is a well-supported extrapolation, not a direct observation, since nothing beyond our cosmic horizon can, even in principle, send us a signal. Eternal inflation is a natural mathematical consequence of the leading models of the earliest fraction of a second after the Big Bang. Models that have made other successful, testable predictions, but eternal inflation itself has not been independently confirmed. The many worlds interpretation of quantum mechanics is a serious, widely discussed reading of a theory that has been tested to extraordinary precision, but it remains one interpretation among several, and no experiment yet devised can tell it apart from its rivals. The mathematical universe hypothesis is the most speculative idea in this entire chain, elegant to some physicists and unfalsifiable to others. It is worth remembering how recently some of these numbers have moved, as a reminder that precision in cosmology is always provisional. For years, the commonly cited estimate for the number of galaxies inside the observable universe sat at around 2 trillion, based on deep, long-exposure images taken by orbiting telescopes and careful statistical extrapolation. More recent surveys, using newer instruments capable of picking out fainter and more distant galaxies than before, have suggested that figure may need to be revised. In some analyses downward, once overlapping and double-counted sources are accounted for more carefully. This is not a sign that cosmology cannot be trusted. It is exactly how the field is supposed to work. Numbers sharpened by better instruments, models updated by new evidence, conclusions held with confidence proportional to how many independent methods agree. Every figure quoted in this script carries that same honest uncertainty, accurate to the best current measurement, but never final in the way a mathematical proof is final. One small, indirect hint may come from an entirely practical corner of physics, the ongoing effort to build working quantum computers. These machines perform certain calculations by exploiting the same superposition that makes a single particle behave as though it is doing two things simultaneously, scaled up to many particles at once, so that in some rough sense, the machine explores many possible paths to an answer before settling on the one it reports. Whether this genuinely supports the idea that those unexplored paths exist somewhere as real branches, or whether it is simply a clever use of ordinary quantum mechanics with no implication for other worlds at all, remains a matter of real disagreement among physicists who work on this daily. It is not evidence in either direction yet, but it is one of the few places where the abstract argument about branching realities brushes up against something being built and tested in laboratories today, rather than only argued about on paper. A related frontier involves pushing ordinary quantum superposition experiments toward larger and larger objects. From single photons to molecules made of hundreds of atoms, toward current laboratory attempts at suspending tiny mirrors and small crystals in delicately balanced quantum states. Any theory in which the wave function genuinely collapses at some specific physical scale, rather than simply branching forever the way Everett proposed, would need to show its effects somewhere along that widening scale. No experiment has yet been sensitive enough to catch a difference, but the gap between what quantum mechanics has already been tested on and the scale at which collapse theories and branching theories start making genuinely different predictions has been shrinking. Steadily for decades, the kind of slow, patient narrowing that has settled other difficult physics questions before. There is also a genuinely difficult mathematical problem hiding underneath all of this, one that researchers openly admit they have not solved. If there are infinitely many versions of a given event happening across an infinite space or an endlessly branching set of quantum outcomes, ordinary probability stops behaving the way it does in everyday life, because comparing the size of two different infinities is not the same as comparing two large but finite numbers. Take something as simple as the set of even counting numbers compared to the set of all counting numbers. Ordinary intuition says there should be exactly half as many even numbers as there are numbers altogether, and in a certain everyday sense, that feels obviously true. But mathematicians compare every counting number with exactly one even number, 2 with 4, 3 with 6, 4 with 8, continuing forever without ever running out of partners on either side. Which means, by the strict definition mathematicians use for comparing the size of infinite sets, both collections are exactly the same size. Depending on which definition of how many you reach for, the honest answer to a question that sounds this simple can come out completely differently. The same ambiguity infects any attempt to ask what fraction of copies of you, spread across an infinite universe or an endlessly branching wave function, made one choice rather than another this morning. Without a rigorously agreed-upon way to compare infinite collections of outcomes, a question phrased in ordinary language, "How likely is it?" may not have a single well-defined answer at all, a genuinely awkward position for any theory that hopes to make testable predictions. Physicists call this the measure problem, and it means that some of the predictions this entire picture seems to make cannot yet be stated with full mathematical rigor. This is not a reason to dismiss the idea. It is a reason to hold it the way careful scientists hold any genuinely difficult question, taken seriously, argued over honestly, and not yet closed. Layered underneath every one of these claims sits a further, unresolved question about whether subjective experience itself is the kind of thing that can be meaningfully duplicated at all, a question belonging as much to philosophy of mind as to physics, and one that no amount of further cosmological measurement will settle on its own. It is worth remembering, too, that plenty of very ordinary-seeming physics remains genuinely unexplained, even without invoking anything as exotic as other universes. Something like 85% of all the matter pulling galaxies together through gravity does not shine, does not absorb light, and has never been directly detected in any laboratory, known to physicists only through its gravitational effects, and referred to, honestly, as dark matter precisely because nobody yet knows what it actually is. A separate and even larger share of the total energy budget of the universe is tied up in whatever is driving space to expand faster and faster, referred to with equal honesty as dark energy, a name that describes the observation rather than an explanation for it. Both of these remain unresolved after decades of dedicated research by thousands of scientists. Mentioning them here is not a distraction. It is a reminder that even the ordinary, single-universe version of cosmology, set entirely aside from any question of distant twins or branching realities, already contains enormous unanswered questions that current physics is still working through patiently, one measurement at a time. It would be misleading to present any of this as settled consensus, because a real and serious disagreement exists among physicists about whether these ideas belong inside science at all. Some cosmologists have argued openly, in published scientific commentary, that a theory whose central claims can never be checked by any observation, even in principle, starts to resemble philosophy, wearing the vocabulary of physics, and that accepting such theories on elegance alone risks weakening the standards that have made science reliable in the first place. Other physicists, equally accomplished, respond that plenty of well-accepted physical claims already sit beyond the reach of direct observation. The interior of a black hole being one example, nobody seriously disputes, exists, even though nothing from inside one can ever be observed from outside, and that the right standard is not direct observability, but whether a theory is well-motivated, mathematically consistent, and connected to other parts of physics that have been tested. Some of this disagreement traces back to a standard set decades ago by the philosopher Karl Popper, who argued that a genuinely scientific claim must be capable, at least in principle, of being proven false by some observation, and that claims immune to any possible disproof belong to philosophy rather than science, however dressed up in equations they might be. Applied strictly, that standard puts real pressure on ideas like the mathematical universe hypothesis, or on distant regions of an infinite universe that can never send us any signal at all. Applied too strictly, however, the same standard would also rule out plenty of physics nobody seriously doubts, including large stretches of what modern cosmology already claims about the very early universe, moments that no instrument will ever directly witness either. Where exactly to draw that line remains a genuinely contested question inside the philosophy of science itself, not just inside cosmology. That in itself says something worth remembering, that the honest state of this subject is an open argument among careful people, not a settled fact waiting to be repeated. None of this means the question is permanently closed to evidence. There are a handful of ways these ideas could, in principle, leave a trace that instruments might actually catch. If our own pocket of space ever collided with a neighboring pocket produced by eternal inflation, sometime in the distant past, the impact could have left a faint, ring-shaped imprint in the cosmic microwave background, a pattern subtly different from the smooth randomness expected otherwise. Several research groups have searched the existing data for exactly this kind of signature. A few tentative candidates have been reported, but nothing has held up to the level of scrutiny needed to call it confirmed. And the search continues with newer instruments. 2 upcoming projects could sharpen this picture considerably. A new generation of ground-based observatories, designed specifically to map the faint polarization patterns left in the cosmic microwave background, aims to detect the gravitational imprint that inflation itself should have left behind, a signal that would help confirm or rule out entire families of inflationary models, including whether the eternal version is likely. Separately, a space-based gravitational wave observatory, currently planned for launch sometime in the 2030s, would listen for ripples in spacetime, far too faint and far too low in frequency for ground-based detectors to catch, potentially reaching back toward the very first moments after the Big Bang, moments no telescope built to capture light will ever be able to see directly, because the universe was still too dense and too hot for light to travel freely. Neither project can prove that other pockets or other branches exist, but both could tighten the constraints on the theories that predict them, the same slow, careful process that turned other once speculative ideas, the bending of starlight around the sun, the existence of black holes, into confirmed features of the universe we live in. If either project someday reports a clean, unambiguous signal in favor of one specific model of inflation over its many competitors, the honest confidence behind tonight's argument would shift accordingly, sometimes strengthening it, sometimes narrowing which version of it remains plausible, exactly the way good science is supposed to move. There is something worth noticing in how often this exact pattern has repeated throughout the history of astronomy. People once assumed the sun was the single fixed center of everything, a light meant only for this one world. Then it turned out to be one ordinary star, among roughly 200 billion others scattered through the disk of the Milky Way alone, an average, unremarkable ball of hydrogen and helium, currently about halfway through a burning lifetime, expected to last around 10 billion years in total. The galaxy containing it turned out to be one among something like 2 trillion galaxies within reach of our best telescopes, most of them containing comparable numbers of stars of their own, an amount of ordinary stellar material that no single mind, however carefully trained, can genuinely picture all at once rather than simply accept as a written figure. People once assumed the Earth was the only planet, a single stage for a single story, until a dedicated space telescope launched in 2009 spent nearly a decade quietly staring at a single patch of sky, watching for the faint, repeating dimming that happens when a planet crosses in front of its star. That one mission alone confirmed thousands of planets around other stars, enough to let astronomers estimate that planets are not rare exceptions, but the ordinary rule, with most stars in the galaxy likely hosting at least one world of their own. Every time the universe has turned out to be more abundant than it first appeared, the immediate reaction has been a small sense of loss, followed eventually by a deeper appreciation for what abundance actually reveals, that the universe does not need to make anything rare in order to make it worth paying attention to. The same logic may apply here. If another arrangement of atoms exists somewhere, thinking something close to these same thoughts, it does not reach into this room and take anything away from what is happening here. The warmth of this particular evening, whatever it is you are doing while this plays, the specific, ordinary weight of your own day, none of that becomes less real because a variation of it might be happening somewhere else, at a distance too large to write down, or in a branch too disconnected to ever reach. What changes is only the backdrop, the size of the stage this moment happens to be standing on, not the moment itself. It helps, too, to remember what the atoms in question are actually made of. It helps, too, to remember what the atoms in question are actually made of. Iron of the kind carried inside your blood is only produced in meaningful quantities during the final, catastrophic collapse of a star, many times more massive than the sun. An explosion so bright that for a few weeks it can outshine every other star in its entire galaxy combined, scattering newly forged elements outward across hundreds of light years in every direction. The calcium holding your bones together and the iron carried inside your blood were not created here. They were forged inside the cores of stars that finished burning long before the sun ever formed, then scattered outward when those stars came apart, drifting through space for billions of years before gravity eventually gathered a small portion of that scattered material into a planet, and then, much later, into you. In that sense, the raw material of a person was never unique to begin with. It was recycled from a shared, galaxy-wide supply, used before in other stars, other clouds of gas, other configurations that no longer exist. What makes the particular arrangement sitting here tonight worth anything is not that its atoms are one of a kind, because they never were. It is the arrangement itself, the specific, unrepeatable pattern of experience that this exact collection of matter happens to be living through right now. There is also something quietly grounding in the fact that none of those other versions, if they exist, can help you, and none of them need to. Whatever is happening in a distant, unreachable pocket of space cannot ease a difficult day here, and it cannot take credit for a good one either. The life actually being lived, the one experiencing this exact sentence right now, is the only one you will ever have direct access to, and that is never depended on whether it happens to be the only copy in existence. It only ever depended on what you do with it. There is a dimension to all of this that is easy to overlook, because it is tempting to picture the multiverse, if it exists, as something that happened once, long ago, and simply left a very large amount of space behind. But if eternal inflation is correct, the production of new pockets of space is not a finished event sitting in the past. It is still happening, continuously, everywhere that inflation has not yet ended, which under this model is nearly everywhere, since our own pocket is a comparatively small, finished patch inside a vastly larger process that has never stopped. New pockets, each starting their own Big Bang, each beginning their own 13.8 billion year clock, or something entirely different depending on where their physics lands, are being generated right now, at this instant, in numbers that never stop growing, because the process that ends inflation locally has never managed to end it everywhere. Under this view, the universe is not simply old, it is still being made. Underneath everything discussed tonight sits a question that no equation has ever managed to answer, one that philosophers were asking long before any telescope existed. Why is there a universe at all, rather than nothing whatsoever? Every argument tonight, the flatness of space, the branching of the wave function, the landscape of possible physical laws, assumes that something already exists for the mathematics to describe. None of it explains why existence itself got started in the first place. The mathematical universe hypothesis offers one attempt at an answer, suggesting that mathematical truths do not need a further cause to be true, the same way a statement like 2 + 2 = 4 does not depend on any physical universe existing to check it, and that if physical existence is simply what a sufficiently complex mathematical truth feels like from the inside, then something existing was never really in question at all. That answer does not fully satisfy everyone who hears it, and it probably should not, because it only pushes the mystery back one more layer, toward the question of why mathematical truth itself is the kind of thing that exists. Nobody currently has a complete answer to that either. It remains one of the genuinely open questions sitting underneath modern physics, patient, unresolved, and honestly stated as exactly that. If any of this has left a slightly uneasy feeling sitting somewhere in the chest, that reaction is worth trusting rather than pushing away, because it usually fades on its own once the ideas have had time to settle, rather than needing to be resolved all at once tonight. Nothing discussed here requires an immediate answer. Cosmologists themselves have spent decades sitting with these same questions without needing to reach a final, comfortable conclusion before continuing their work, their evenings, their ordinary lives. There is no obligation to arrive at certainty by the end of this sentence. There is only an invitation to notice how much larger and stranger the space around an ordinary life turns out to be, and to let that sit quietly alongside everything else already carried, without needing to carry it any more heavily than that. There is something worth noticing in the fact that this exact idea is not being encountered alone tonight. Somewhere else right now, someone else is hearing roughly this same argument laid out, in a different voice, in a different room, arriving at roughly this same mixture of unease and curiosity. That has always been true of any idea worth sharing. Long before any physics about distant twins entered the conversation, a thought passed from one mind into another is never really a single, solitary event, and it never needed to be, for the thought itself to matter to the particular mind holding it. Nothing about tomorrow morning changes because of anything said tonight. The coffee will still need making. The same ordinary tasks, the same familiar faces, the same small decisions about how to spend a given hour will still be waiting exactly where they always are. That is, in its own way, the most reassuring part of all of this. An idea this large was never going to rearrange the practical shape of a single day, and it was never trying to. What it offers instead is something quieter, a way of holding that ordinary day with a slightly wider sense of what it is actually made of and where it actually sits. It is worth admitting plainly that a question this large may not be fully answered within any single human lifetime, including the lifetimes of the physicists currently working hardest on it. Some of the deepest open questions in physics have taken generations to resolve, passed from one researcher's working notes into another's, refined slowly across careers rather than settled in a single dramatic discovery. The people building the next generation of telescopes and gravitational wave detectors mentioned earlier are, in a real sense, working on behalf of researchers who have not been born yet, laying groundwork for conclusions that may only become clear decades from now. The same way earlier generations of astronomers spent entire careers cataloging the positions of stars without ever knowing that data would eventually help confirm the expansion of the universe itself. There is something worth admiring in that kind of patient, multi-generational effort, a willingness to contribute honestly to a question, knowing the final answer might arrive only for someone else to read. That patience is available in an ordinary life too, in a smaller and more personal way. Not every question needs resolving before the next task gets done. Not every uncertainty needs to be settled before dinner gets made, before sleep arrives, before tomorrow begins, in whatever ordinary shape it happens to take. The scale of tonight's subject was never meant to be carried the same way a grocery list gets carried, checked off, completed, set aside. It is closer to something held loosely in the background, returned to occasionally, allowed to deepen slowly over years, rather than resolved tonight in a single sitting. Different people, hearing all of this laid out the same way, tend to land in genuinely different places, and neither response deserves to be argued out of someone. For some, the pull toward comfort is strongest, the sense that nothing meaningful is ever truly lost if some version of every path gets lived out somewhere. For others, the pull runs the other way, toward a sharpened sense of how much weight sits inside the one branch actually being lived, precisely because it is the only one any given mind will ever have direct access to. Both reactions are reasonable responses to the same honest set of facts, and neither one is required in order to have understood the physics correctly. Even the word universe starts to strain a little under the weight of everything discussed tonight, since it was originally coined to mean the whole of everything, a single, complete totality with nothing outside it by definition. Cosmologists now often reserve that word for our own observable patch and whatever ordinary space lies beyond it, while reaching for other terms, multiverse, landscape, wave function, to describe whatever larger structure might contain it. That is not a sign of confusion. It is simply what happens to language when the thing it was built to describe keeps turning out to be only part of something larger. A pattern that has repeated at almost every major turn in the history of astronomy and shows no clear sign of stopping here. There is a difference worth naming between finding this idea unsettling and finding it diminishing, because the two reactions are not the same, even though they often arrive together at first. Unsettling is a reasonable response to learning that the universe is far larger and far stranger than daily experience ever hints at. That reaction fades with familiarity, the way the vastness of the night sky stops feeling frightening once you have spent enough evenings simply looking up at it without needing to solve it. Diminishing is a different claim entirely. The idea that because something is not singular, it must therefore be worth less. Nothing about tonight actually supports that second claim. A particular sunset is not worth less because the sun has produced billions of sunsets before this one, and countless more will follow. A single conversation with someone you care about is not worth less because conversation, broadly, is one of the most common things happening on the planet at any given moment. Abundance and value have never actually been opposites, no matter how strongly the first instinct suggests otherwise. What tonight offers, more than an answer, is a change in scale. And a change in scale is not nothing. Most of a life is spent operating at a very narrow range of distances and time spans. The length of a room, the span of a day, the reach of a single lifetime. None of that shrinks because the underlying physics turns out to be enormous. The room is still the room. The day is still the day. What changes is only the frame around it, and frames, quietly, shape how a life gets lived, whether as something small and precarious clinging to a single accidental rock, or as something built from matter old enough to have passed through the heart of a star, embedded in a process of unfolding physical law large enough that variations of this exact moment may be echoing outward across distances too vast for any number to make comfortable. None of this uncertainty stops researchers from taking the question seriously, and it is worth understanding why. Physics has a long history of ideas that sat exactly where this one sits now, mathematically compelling, difficult to test, and initially dismissed by much of the field, before better instruments eventually settled the matter one way or another. Atoms themselves were treated by some serious scientists as a convenient fiction, rather than a physical reality, well into the early 20th century, until experiments confirming their existence became impossible to argue with. The expansion of the universe was considered a fringe interpretation of Einstein's equations, before galaxies were actually observed retreating from each other. Grant funding committees, journal editors, and research groups continue investing real time and real money into testing the predictions of inflation and quantum foundations today, for the same reason earlier generations kept building better instruments to test earlier uncomfortable ideas, because an idea being difficult to confirm has never, on its own, been a reliable sign that the idea is wrong. Taken together, the picture assembled across this evening rests on four genuinely different arguments, each resting on a different part of physics, each carrying a different level of confidence. A flat, uniform universe extending beyond our horizon, which is the most conservative claim and the one resting most directly on measurement. An eternally inflating sea of separate pocket universes, which follows naturally from well-tested models of the earliest universe, but has not itself been directly confirmed. A branching wave function under the many worlds interpretation, which uses the same confirmed mathematics of quantum theory without adding an unexplained collapse, but remains one interpretation among several genuine competitors. And a mathematical universe containing every logically consistent structure, the most speculative claim of the four, offered less as an established finding and more as a serious hypothesis worth taking seriously, rather than dismissing outright. There is a simple, ordinary practice that connects unusually well to everything discussed tonight, available to anyone, regardless of how much of this physics they choose to hold on to afterward. Stepping outside on a clear night and simply looking up, without needing to name a single constellation or recall a single number, puts a person in direct contact with the same light this entire conversation has been built from. Photons that left their source anywhere from minutes to billions of years ago, carrying information about a universe that, as far as the best available measurements suggest, likely continues far past where any of that light originated. Nothing about that view requires belief in distant twins or branching wave functions to be worth having. It only requires noticing that the dark spaces between the visible stars are not empty in the way they appear, but are, by the best current understanding, filled with exactly the same kind of ordinary, abundant reality responsible for producing everything discussed tonight, stretching outward in every direction, further than any single evening could ever hope to measure. There is something quietly connecting, rather than isolating, in the fact that whatever else might be happening in some unreachable pocket of space or branch of the wave function, it would still be happening under the same physical laws discovered here, the same gravity, the same chemistry, the same handful of particles arranged according to the same equations that describe everything measured from this one small planet. Distance and separation are real, but the laws themselves, as far as any measurement has ever shown, do not stop at any boundary, which means that even an unreachable twin remains, in the deepest sense physics can offer, made of the same universe rather than some entirely foreign one. Even the act of trying to hold all four of these arguments in mind at once, the flat geometry, the eternal inflation, the branching wave function, the mathematical landscape, says something about how much has changed in a relatively short stretch of scientific history. Less than a century ago, the prevailing assumption among most astronomers was that the Milky Way itself was the entire universe, a single island of stars surrounded by nothing at all. That assumption held until better telescopes revealed countless other galaxies scattered far beyond our own, each one its own island of billions of stars. The same pattern of quiet correction has repeated at every larger scale since the observable universe turning out to be only a fraction of a much larger whole, that larger whole possibly repeating itself without end, and the mathematics describing all of it, possibly pointing toward a reality stranger and more abundant than even that. There is no reason to assume this particular pattern of correction has finished playing out. The honest position, the one every measurement mentioned tonight actually supports, is that the universe has consistently turned out to be larger, older, and stranger than whatever the previous generation assumed, and there is little reason to think this generation has finally reached the end of that pattern. It is worth ending on the same note the whole subject actually began with, back when a single measurement of triangle angles hidden inside the afterglow of the Big Bang first suggested that space might never curve back on itself. That single number, gathered by instruments built to detect differences smaller than any human sense could register, opened onto a landscape of consequences no one designing the instrument had originally set out to explore. Distant twins, branching wave functions, landscapes of possible physical law, mathematical structures existing in their own right. Good measurements tend to do that. They rarely answer only the question they were built to answer. They open onto neighboring questions nobody had quite thought to ask yet, which is, in the end, most of what makes this kind of inquiry worth continuing. If there is a single thread worth carrying away from tonight, it may not be any specific number or any specific interpretation of the mathematics, all of which remain open to revision as better instruments arrive. It may simply be the willingness to keep asking the question in the first place, the same willingness that pushed early astronomers to keep pointing better instruments at the sky long after they had already answered enough to satisfy ordinary curiosity, and the same willingness that keeps today's physicists building satellites, gravitational wave detectors, and careful mathematical arguments about problems that may not be resolved for decades. That willingness has never required certainty up front. It has only ever required a genuine interest in finding out, and a patience with not knowing yet, which may be the most honest attitude available for a question this large. It is worth remembering, before closing, how ordinary the tools behind all of this actually are. No exotic new sense was required to measure the flatness of space. Only patient light collecting instruments pointed at the same sky anyone can look up at. No new law of nature was invented to justify the branching of the wave function. Only an old and thoroughly tested law taken at its word rather than quietly edited to feel more comfortable. No leap of faith was required to imagine pocket universes forming endlessly. Only the same inflationary mathematics that already correctly predicted the fine details of the light left over from our own Big Bang. Everything discussed tonight grew out of ordinary scientific caution, following the evidence rather than personal comfort. Wherever that evidence happened to lead, even into territory this strange, that kind of caution is worth carrying forward past tonight, into whatever comes next in this slow, ongoing project of trying to understand where we actually are. The universe has never owed anyone a comfortable answer, only an honest one, gathered patiently, checked repeatedly, and held loosely enough to be revised the moment better evidence arrives. Whatever the final shape of this picture turns out to be, flat and endless, curved and finite, branching endlessly at every quantum event, or something else entirely that no one currently working on this has thought to propose. The process that gets us there will look exactly like the process that got us this far. Careful measurement, honest disagreement, and a patient willingness to let the evidence speak louder than any single expectation about how the story should end. This entire evening rests on evidence collected across generations of careful, patient work, and it deserves to be received the same way that work was done, without rushing to a final verdict simply because a conclusion would feel tidier than an open question. So the honest answer, gathered from the most careful measurements cosmology has ever produced, is that the universe is almost certainly far larger than anything we will ever see, shaped in a way that makes repetition, somewhere out there, difficult to avoid mathematically. Whether that repetition takes the modest form of a distant twin built from the same finite arrangement of atoms, or the stranger form of endless pocket universes with their own laws, or the stranger still form of a wave function branching every time a single particle makes a choice it did not have to make, is a question current physics has not finished answering. What it has answered, clearly and repeatedly, is that the universe was never as small or as centered on any one place as it first appeared to be. If you have made it this far, thank you for spending this quiet stretch of time in the company of an idea this large. If any part of tonight gave you something to sit with, consider leaving a like and subscribing. It genuinely helps this channel keep making these journeys. Wherever you are right now, whatever this particular version of your life looks like tonight, let it be enough to simply rest here, inside this one arrangement of atoms, in this one corner of an unmeasured universe, and let your thoughts go quiet.